So the cabezon is an uncouth, repulsive-looking fish, dark greenish brown, the body larger in proportion to the head than other sculpins, but it is of good flavor, either boiled or fried. That's how James G. Swan, a 19th century US anthropologist, first described cabezon when he was introduced to one in 1868. Today we might be a bit more charitable. A more contemporary description could be that it's a seafloor-dwelling fish that lives in and around rocky reefs, kelp forests, and other nearshore habitats all along the Pacific coast. One thing Dr. Swan does get right, though, is that cabezon are delicious. And as such, they remain to this day quite a popular fish among fishermen, even with some commercialized fishing occurring along the coast as well. And because people like to catch and eat them, cabezon need management to ensure they're caught sustainably. That means things like limits to how many fish you can catch, how big a fish needs to be before it can be caught legally, and when seasons are open for fishing. For cabezon, this has historically been the responsibility of the federal agency NOAA Fisheries, who conduct assessments to understand how healthy the fish population is, and in turn, set what those limits should be. However, this responsibility was recently delegated to the state, who manage the nearshore waters where cabezon are more typically fished. This means that cabezon and a number of other species will no longer undergo the standard federal assessment of their population health. For cabezon, the most recent assessment of this type is from 2019, which leaves us with a management gap as the state is left to catch up with its new responsibilities. In the meantime, then, we have a species that is still fished for, but for which there is not a formal population health assessment to proactively inform how much fishing should take place or when. Especially as climate change continues to impact coastal ecosystems, filling this kind of management gap will only become more important. So for this project, I started with a simple question, which was, can the data we already have be used to learn something useful about this fish and inform its management to fill that gap? One place to start with a wealth of fish data is the California Cooperative Oceanic Fisheries Investigations Program, or its friendlier name, CalCOFFI. This partnership between Scripps, NOAA Fisheries, and the California Department of Fish and Wildlife is one of the longest running ocean monitoring programs in the world. Since 1949, CalCOFFI ships have been surveying this grid off the California coast on a regular schedule, towing nets through the water and counting what comes up at each of the stations marked here by the black circles. What they count includes the eggs and larvae of hundreds of fish species, including cabezon. They also take measurements of ocean conditions at each sampling station, like temperature, salinity, oxygen, things like that. What CalCOFFI gives us then is a pretty remarkable record. Over 75 years of consistent observations about biology, biodiversity, and oceanography off the California coast. To answer our question then of how to inform management with these data, we used about 35 years of this record on cabezon larvae and ocean conditions, during which time sampling was steady and uniform. We stayed within a nearshore region for our data, marked by this red border, which is generally where we'd expect to find these larvae. And the idea was, if we can understand patterns in larval cabezon distribution and abundance, maybe that could tell us something about the adult cabezon that we want to fish and eat. So to do that, we had to build this 35-year picture of these larvae. So I had the data, and now I had to see if it could tell us anything useful about cabezon over that time period. So I built some statistical models to estimate a couple of things. First, across the coast, where do we see those larvae? So this map shows that bordered nearshore region. The lines and dots are the sampling grid and stations we just saw. And what our model does is it estimates what the distribution and abundance looks like across each year, across that whole space, using the data picked up at each of the stations. So when you remove the lines, you can see it a bit more clearly. That brighter orange-white color means more larvae, and the darker purple means fewer. So you can see this bright patch in the northwest, where we estimate the highest concentration of cabezon larvae to be, fading into darker areas with fewer larvae as you move further southeast. The second thing I modeled was how many larvae do we see over the 35 years. So if you tally all the cabezon that you predict in each of those annual maps, you get a number for relative larval abundance each year. So in that figure on the right, we see that relative value of abundance, shown on the vertical axis, changing over time, rising or falling from each year from 1981 to 2015. So these results gave me some solid signals from the cow coffee record. For cabezon, I now have estimates for where and how many cabezon larvae are in Southern California over that 35 years. And the first thing I thought to try with these results was to tie these larval signals directly to the adult population that managers and fishermen care about, using that last formal assessment from 2019. And the logic goes something like this. A strong year for larvae should show up as a similarly strong year for adults, because the more spawners you have in the adult population, the more larvae you're likely to see. Alternatively, a strong year for larvae could also show up a few years down the line as a strong year for adults when those larvae have matured. Cabezon take a few years to mature into adults, so we might expect larvae to track with that population some years later. If these relationships held, it would almost be plug and play. See how many larvae there are now and use it to estimate adults now or to predict adults in a few years and set your limits accordingly. Unfortunately, when we tested the relationship between our larval estimates and estimates of adult abundance, they did not track well. But if you think about it, that makes a bit of sense intuitively. Fish eggs are quite fragile, and there are a lot of threats that they have to face when hatching into larvae, then maturing into juveniles, and then into adults. You've got predators, ocean variability, the availability of good habitat, and so on, all of which will impact whether a given cabezon survives into and then past its larval stage. You might expect then that there's some decoupling between how many spawners and larvae we see in a year, and then again, how many of those larvae survive over the next several years into adulthood. So our 35 years of data on larval cabezon don't tell us much about adults, at least not in a way that would directly link to something like fishing limits or seasons. But they do tell us something about the conditions in which larvae are found. So the where and the when made me ask about the how. We'd seen patterns in distribution and abundance and wanted to know what was driving those patterns. In other words, could the same data reveal something about how cabezon larvae respond to the ocean around them and whether that shapes their distribution? And there the answer seems to be yes. So two relationships stood out clearly when I dug into this question. One, cabezon larvae are more likely to be present in cooler water. So in this plot, the bottom axis is sea surface temperature, and the vertical axis is how likely we are to find a larva. So our blue line sloping up means that we're less likely to see larvae the warmer it gets, sloping down, excuse me. And two, cabezon larvae are more likely to be present in more oxygen-rich water. So this is a similar plot, except that the horizontal axis is now showing us dissolved oxygen content in the water instead of temperature. So this time the green line sloping up tells us that the more oxygenated the water is, the more likely we are to see a larva. So a small change, could be a few degrees Celsius or a small shift in oxygen content, makes a real difference in whether cabezon larvae are likely to be present in a given area. And so what does this mean for filling that current management gap for cabezon? We know that the cow coffee record can't forecast adult cabezon, so we can't use it to do something as concrete as inform fishing limits. While that forecasting ability would have been nice to have off the bat, this finding does give us a useful bound on how this kind of long-term larval data can fit into management for cabezon. Specifically, it shows us what conditions larvae depend on in their fragile early life stages: cool, oxygenated water. While more research is needed, we might anticipate that if those conditions decline, so might cabezon. That makes these results compelling as a climate vulnerability baseline, telling us what to pay attention to when considering the full life cycle of cabezon and how they respond to changing ocean conditions. Because even a healthy population is held up by several things at once, and favorable conditions are one of those things. So if those conditions decline, the population may not collapse, but there's one less thing holding it steady. And ultimately, it's about cabezon, but it's not just about cabezon. So these conditions that cabezon larvae are responding to are exactly the conditions changing off the California coast. This region is expected to undergo some of the most rapid rates of oxygen decline in the world, alongside rising ocean temperatures and more frequent and intense marine heat waves. And cabezon aren't alone in responding to those conditions. research has found similar patterns across other nearshore species. And that suggests something more profound about how an ecosystem is responding to its environment rather than any individual species in isolation, and how that ecosystem might be impacted by changing ocean conditions. So what we're seeing then is more than just a cabezon story. We're seeing a signal that a changing ocean could shape where and how many fish are born before they even begin that difficult journey into adulthood. And so let me bring us back to the question I opened with. What did 35 years tell us about cabezon? And the honest answer is not quite what we expected, but maybe something more interesting. We can't use our data record to predict adult cabezon directly, so it won't on its own help us set a fishing limit. But the same record does reveal how cabezon respond to a changing ocean, and we know cabezon aren't alone. So the bigger takeaway is this. A data set built over decades to record where we see larval fish turns out to be informative of how those larval fish respond to their environment. The data we already have then can answer questions we might not have thought to ask of it in the first place. And that feels like a great opportunity as we look to fill management gaps and consider ecosystems as a whole, rather than always focusing on a single, uncouth, repulsive-looking species. So I'd just like to give a couple of quick thanks to my Capstone Advisory Committee for their support on this project. Dr. Bryce Simmons, my committee chair and a professor here at Scripps, was an invaluable thinking partner on the modeling and interpretation. Dr. Andrew Thompson at NOAA provided critical methodological support as well, offering ideas and insights drawn from his extensive work on cow coffee and larval data. And Heidi Batchelor, a researcher and lecturer here at Scripps, was just as generous with her time, ensuring I was on track and thinking carefully about where and how this research should be positioned. And then beyond my committee, I'd just like to thank Dr. Julia Coates at the California Department of Fish and Wildlife and Dr. Eric Ward at NOAA Fisheries, both of whom were also enormously helpful in ideation and analysis. And thank you all for being here and listening to this work. I'd be glad to take any questions.
Are there limits on the size and amount of cabezon that fishermen can take, and how do they catch them? Are they just with fishing rods or nets or what?
Yeah, they're caught primarily with rod and reel. I think they're also a target for spear fishermen. I'm not as familiar with the commercial fishery, but I know that the state does work to set limits now. It's more so a question of how do they set limits down the line when there's less recent information to inform those limits. But yeah, they do have management structures in place.
I've got a question. Why the cabezon? It's so uncouth. What made you choose it?
Yeah, so cabezon is one of 26 species that are no longer going to be managed by NOAA, so it is one of several candidates that we looked at. The reason we chose cabezon was kind of multifold. One, there is a fishery associated with it, so it is targeted, and it is a fishery that presumably requires management of some kind. And it also has that stock assessment from 2019 to serve as a baseline. So when you're doing these kinds of spatiotemporal studies, you can really line it up to something that is a standard. And then lastly, there's a lot of data on them from cow coffee, so there's a solid record to look from.
Hi, that was amazing. Can you give me some insight on how, if you know, did the federal government decide which species were going to move from federal to state management?
Yeah, so that's a good question. I think that mostly the rationale was that a lot of these fish, including cabezon, are more typically found in nearshore waters, and there's a management delineation between the states and the feds at 3 miles offshore. So if you primarily find fish within that 3-mile radius of the shore, you might say that's a better candidate for state management, which was the case with most of these fish species that were removed from federal management.